Hello everyone, how are you? My name is Jiri and today we have an interesting topic because we are going to discuss acceptable planning and influencing individual behavior to reduce transportation energy expenditures of a city. My name is Jiri, I'm a data scientist and I'm a stream owner of machine learning in economics with ACE. And I'm very honored to introduce you Shiwali. Shiwali is joining the present. She's joining our session today and will be presenting her research. She is also a researcher at PARC, which is a Xerox company in Palo Alto. Let me also introduce ACE for those who watch the stream for the first time. We are called Aggregate Intellect Socratic Circles, and ACE is a community of machine learning practitioners and researchers who have gathered around three topics in AI. That is research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, visit ai.science and log in to have access to slides from this and other sessions and many more. Please make also sure that you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. We currently have about 15 different streams that are focused on various machine learning topics, and this is machine learning in economics. I hope you will enjoy it and come back. Also, I want to provide a very short motivation why you should watch this presentation and listen to what Shiwali has to say. And I maintain that the choice modeling is an evergreen topic in behavior economics that has been modeled and explained through cognitive sciences, but recently more advanced and accurate machine learning approaches have been proposed. This is a machine learning in economics stream, and I want to focus, I maintain that this session is important because in economics we were taught about externalities. For those who don't know what externality is, externalities are either positive or negative byproducts of human behavior that affects other people or entities in economies. For example, a paper mill may pollute a local river, which is a negative externality to the inhabitants. A very similar case is transportation and commuting in large cities, as the activity consumes a lot of resources. Traffic jams and air pollution are both negative externalities locals must deal with. Traditional economic theories teach us to introduce or put into practice restrictive policies and other interactions to make a positive impact. However, I believe the most effective change must come from the bottom. The rising question is whether machine learning can help the cities and local people to commute at lower transportation expenditures. However, humans are selfish machines, so we must bring a solution that is acceptable and alternatives can be considered by the single user. Again, we are having session focusing on choices, but this one is a little bit more different as it concerns a hot topic every large city encounters. Moreover, using machine learning for social good is something ACE already covers, but I'm happy to have Shiwali here with her interpretable approach how to tackle the issue with machine learning. She also designed a nice framework that policymakers should consider if they wanted to design effective policies. Shiwali, I'm passing my word to you. Thank you for joining us.
Thank you, Jiri, for having me. I'm very excited to be talking to you and to Aggregate Intellect and all the people who may be watching. So hello from California. Hi. So, Jiri, should I just start? Okay.
You are ready to start.
Okay. So I'm a senior Thank you, Jiri, for that introduction. And thank you for highlighting the push on doing social good, right? working towards improving public welfare, because I think as AI scientists, this should be one of our goals. A lot of the times when people hear about AI methods, AI solutions, everyone gets scared that, hey, it's going to take all our jobs, or it's going to build autonomous killing machines. But as AI scientists, if we adopt doing good as a goal, I think we can have a great impact on our society. And that's what really motivates me as an AI scientist. I'm a senior member of research staff at Palo Alto Research Center. And for people who may not know it, it's one of the oldest industrial research labs that were established when computers were just in their infancy. And Palo Alto Research Center built its name in trying to, in being the first sort of human-centered technology labs, right? A lot of the work that we did helped computers become so common in our society. And one of the research agendas that we are following at PARC is like, now AI is becoming really big. So how do you make sure that it fits really well in our society? So this is the work that I'm presenting. It was published at the Journal of AI Research in their AI and Society track. So this is one of the top AI journals. And what you're going to see is not just a flavor of machine learning, but also other AI techniques. Okay, so jumping right in, the problem that we are trying to study is energy consumption and transportation. Transportation is one of the largest consumers of energy, and some estimates say that around 30% of energy in the US in 2016 was spent on transportation, and this is a really big number. The US is one of the top energy consumers in the entire world, and 30% of the energy consumption is coming from transportation. And it's far from efficient, right? So we all have experienced congestion on roads, and some roads are just really open, others are congested. So we have not efficiently using the transportation network that's being built, and it weighs around 6 billion hours every year and 3 billion gallons of fuel. And this is a lot. Like if we are currently hurtling towards a climate crisis, and if we continue operating like this is just completely unsustainable. So ARPA-E, which is a government research agency in the US that's focused on energy, created this program called Transnet that ran from 2013 to 18. And the whole goal of the program was to use the latest AI machine learning techniques to then figure out how do we solve this consumption problem? How do we use technology to then reduce the energy consumption in transportation? So PARC was one of the research labs who were studying this problem. And our idea was a little bit different from a lot of the other teams who were competing with us on this program. Our idea was that, the transportation space has changed a lot. So people, it's not like the only choice to go somewhere is driving or taking the bus, but it's also like there are a lot of companies who are now have e-bikes, so you could rent them, for the last mile transfer. You have a lot of carpool options. There are buses with you, because there's a lot of things that have really changed our transportation landscape. So our question was like, if we could recommend so you imagine like something like Google Maps, so you're trying to go from point A to point B, right? Instead of just telling you here's the driving route, here's the bus route, could it like combine parts of it as a driving thing? So you drive to the nearest train station, then you take the train, and then you maybe rent a bike from there and go to your office, right? If it could do some of this multimodal planning that's aimed at reducing the energy consumption of a city. The sort of problem is the humans of the system, right? I could come up with the most energy efficient plan for you, but what if you don't really like it, right? You're not going to accept it. So what we really focused on was this human aware part of it. We want to understand the humans of the system, what is that they like, what is it that they don't like, and then use that information to then do path planning such that we are trying to reduce the energy consumption of a city. So that was our approach, and it can be contrasted with like other more economics-based approach where you're trying to incentivize people by giving them money to take some low energy route. The problem with those kinds of incentivization schemes is like as soon as you remove the incentive, the behavior shifts back to the normal. Right, so we really want to study what goes inside humans' choices, and then leverage that to then do path planning, so that we don't really have to rely on this external incentive, but rely on, use humans' internal incentives and motivations to then influence them to take less energy costly plans. So that was our overall approach. In the paper, we describe how the influence problem can be framed. So imagine there's Dr. Jane, who really cares about, and say we know something about her, right? She's employed, she cares about the environment, she values her free time to travel. We know something about her transportation network, right? We know that she lives a mile away from the train station. We know that she has a car. We have her access to her calendar, so we know that okay, she has to reach work by 9 a.m. The question is, by combining all of these pieces of information, can you then come up with a message or recommendation to Dr. Jane that really influences her behavior? So right, it could be that it has to be scheduled at the right time, right? As soon as she's about to leave for work, you have to tell her, hey, at 8:45, hey, you should be thinking about these other sustainable transportation choices available to you. It has to be acceptable in that we really are designing this recommendation for Dr. Jane, right? So if she values free time during travel, then recommending her to take the bus is more likely to be accepted than if you told her that she should be taking a bike, right? Because when she's riding a bike, she doesn't really have free time. So knowing this about Dr. Jin is useful. And then maybe we want to frame it in a compelling way that she actually accepts it. So maybe we want to say that that if she takes this option, she will contribute to reducing emissions by 10%. Say like she's someone who is very, empirical, cares about the environment. So you have to like change the way you frame the message as well. So the paper defines the influence problem, and then the rest of the technical approach looks at acceptable planning, like what makes a recommendation acceptable to a person. And to do this, we bring together two very diverse disciplines. One is coming from AI philosophy, which is like AI planning. And just to really quickly go over for people who may not know it, like you want to go from point A to point B, and there are different ways of going there, right? You could take the bike, then take the train, then take the lift, or you maybe drive, then you park, then you take the train, and then you use a bike share. So there's different ways in which you can go from point A to point B. So you can consider a graph that you goes from origin to destination. It has multiple edges between all these transfer points. You can come up with a regular expression that constrains the graph based on what resources someone might have accessible to them, right? So if someone doesn't have a bike, then this edge is not accessible to them. So once you have a graph, you have constraints over that graph, then you can start and you also want to measure, cost of each edge. So if you care about energy, you might want to say, okay, going from point A with biking to the intermediary point doesn't take any energy, so the energy cost there is zero. You can also have a time cost. So basically your planning approach will give you a path that minimizes to whatever your cost function is, and in the cost function you can include energy, time, and things like that. So you can use this method to figure out what's the most energy optimal, time optimal plan for people. So that's where we started from, and this is like very regular in AI literature. The other part that we started from was this behavioral economics theory from, rational choice theory, which is trying to study, well, why do people behave a certain way? Well, how do they choose, right? So you have, as a traveler, you have a set of alternatives that are available. So you have car, walking, bus, train. Each of if you make this choice, each of these choices has certain utility for you as a person, right? So part of that utility is dependent on the mode. So it would be things like cost and distance traveled on that mode. The other would be person dependent, right? It would be income, education, and things like that. So the utility of that choice is dependent on a variety of different attributes, and the theory says that a linear combination of those really goes into theory. And if you apply the principles of probabilistic utility maximization, that humans are rational beings who are trying to maximize their utility, and then you apply the logistic assumption about modeling, you would get to this really nice probability framework around choice, right? So the probability that you will choose option I is dependent on what ratio of utility it has given all total utility of everything that's given to
And I have a question here.
Yes.
So for those, because a lot of people can join us who are not familiar with economics, can you explain us what is utility?
So utility would be something like how useful a certain thing is, right? So there's this internal notion, it's never expressed, but how it's expressed is the way you make your choices, right? So for example, if I am, a scientist who's trying to study environment, for example, then the utility of reading environmentally related literature is very high for me because it gives me benefit versus reading, some other kind of literature, for example, news, right? So I have a constrained resource, my time, and I'm trying to choose between like which choice I want to spend my time on, and the choice is dependent on something that is true about me as a person and also about the choice, right? So that's the overall broader idea of what utility is. Utility is something that drives our decisions, right? So you can think of it as a number that then then it leads to us making a specific choice about a certain resource that we may have. Jiri, was that useful, or do you want to put something?
Yeah, no, this is very fine. I would just summarize it that the utility is the benefit we get.
Yeah.
So you can consider it as it like that.
Right. It's a person's expectation of the benefit, which then goes into their choice of why they're doing X or Y.
100% agree. Thank you.
So then, like, we talked about these two different pieces of modeling. The question is, like, how do you put them together? They originated in different streams. One came from AI research, but the other came from economics. The question is, like, how do you put them together? So there are two questions that the paper studies about putting them together. The first thing is defining what does acceptability mean, right? So if you remember, the choice theory says, how probable is Dr. Jane to take a car versus bus? Right now, this question is slightly different from saying, what should, like, Dr. Jane usually drives to her office, would she take the bus if recommended, right? So it's a slight twist on the question, and just we were not sure if the prediction part of the probability choice theory actually was useful in evaluating different choices, like in evaluating if something would influence Dr. Jane, right? So defining what acceptability means was a big part of our research. Then the second was that, hey, there's planning theory that says, this is how you would minimize the cost when you're traversing a graph. There's choice theory that's saying, why do people make certain choices? So like putting them together was a challenge. And so I'll just go through how we did that, and the paper describes that in much more detail. Okay, so the first question is defining acceptability. What would make the recommendation acceptable to Dr. Jane, given that we know something about Dr. Jane, right? So Dr. Jane has a utility for the usual route, right? So assume that she takes her car every day. So taking the car gives her some value, gives her some value, right? Now, if we try to recommend her a different route, that route will have a different value. So we are asking her to give up this value and get this value instead. So what we are asking Dr. Jane to do is to pay a switching cost, right? Presumably she's taking the car because that's just has higher utility than taking the bus. We are trying to say that, hey, you have to pay this switching cost, but then you get something in return, which is, the reduction of cost in the environment. So we are asking Dr. Jane to pay a switching cost whenever we are trying to recommend her a new route. And we inverse that by saying switching cost is inverse of switching gain. So what the hypothesis was that if the higher the switching gain, the more acceptable is the plan to Dr. Jane, and the more likely she is to adopt it. And then we backward computed from the theory, and all we are trying, and eventually what we got to was that it's the ratio of probabilities that matters, right? The probability that a person P will take a route R that's recommended divided by the probability that she will take her usual route given that person is what really gives you the sense of what is the cost she has to pay when we are trying to get her to pick a different option. So that's how we got to a definition of acceptability. Again, we don't really need to fully enumerate the utility. If we can compute the probability that Dr. Jane will take a car versus Dr. Jane will take the bus, then we can assume that we can then start computing how acceptable the bus is to Dr. Jane versus, if we had to recommend her to take the bike. So probability itself is sufficient. And now this is the useful insight, right? If probability by itself is sufficient, we know machine learning methods who compute probabilities, and they are really good at doing it over large data sets. So that was our next step is how do we estimate acceptability? And we proposed a machine learning approach to do it. So we had this data set called Caltrans data set, which recorded single day trips for the entire 2 years from 58 counties in Los Angeles. Right? It has around 5,000 residents from 2,000 households. It's capturing 79,000 trips. So this is a very extensive data set. And what it was doing was like, it was asking, it had people talk about their travel diaries. Like, okay, on Monday, where did you go? Why did you go to, your destination? How long did it take? What mode did you take? And things like that. So we then extracted some features out of this data set so that features were trip related. So the trip distance, how far did people travel, demographics, which was education level, number of people in the household, employment statistics, and then also interesting things like mode accessibility, like how many automobiles does a person has access to? Do they own bicycles? Do they have driver license? Do they have a transit pass? Right. So we have the trip related, but we also have the person related. We have the person-related and the mode-related variables in the data set. There was some mode experience, like do you use transit regularly? Do you make bike trips and things like that? And then there were labels that are interesting, right? So labels are what mode did people take given these features. So there's this extensive data set, publicly available. Governments do this regularly, at least in the US. So then we framed the multi-class prediction problem. So given those features, can you predict what mode a person would take? Remember, right, if we know the predictions, we also know the switching cost, right? Because the difference in utility is the switching cost that influences adoption. So we developed machine learning methods to then do this prediction problem. Here you are seeing two different baselines. We built a random forest for solving this prediction problem. We also did a more deep learning approach, which was a multi-layer perceptron from TensorFlow. And at least the way we had structured the problem, we found that the random forest, it's a standard scikit-learn random forest that was used in the prediction part. That was the one that was giving us the best prediction. And we could have developed a better deep learning model, but remember, like the problem that we're trying to solve was not just prediction itself, but was trying to understand decision making, right? How do we influence Dr. Jane to do something different? So we determined that this prediction is good enough, and then we moved on to the next part. So some takeaways here are classifiers, are really good at at giving us predictive information. They can provide the probabilities for different routes a person would take given their features, right? And because it's a machine learning model, you can combine a wide variety of features. And this is not possible in the traditional, linear regression economic models. Like you don't know how many variables you can combine. Now, because we have a classifier that operates over a bigger input space, you can really, use that part and combine a lot of different kinds of features. So I could take a break here if there are questions. Otherwise, I'll just move on.
Yeah, we can take a break. I see a few people are online here, so I would encourage anyone who has any question to ask the question in the chat. I will be very happy to ask Shiwali. But meanwhile, I also have some questions I prepared. One of the reasons I like your paper is it's very comprehensive, and I find before you move, I'm just okay. Yeah, I will definitely ask this question, but I like the paper because it provides a good framework that could even policymakers can consider. Yes. So my question is, if you, in your research, did you come across how policymakers usually solve these problems?
Yeah, I mean, we did a lot of this analysis because policy, like at PARC, we are trying to study how do we support policy makers' decision-making problem. So the way people usually do it is through these surveys, right? So every year they would conduct these surveys. They would try to measure how many people out of this sampled population are taking the walk, are walking, are taking the car, buses, and things like that. It's a very labor-intensive process. And then they would try to fit some models. They would the other part is which I already talked about is like they might try to incentivize with money, right? That's the first thing. Like, hey, your work will give you free tickets if you take the bus, or we would pay for, your bike if you take the bike every day, right? So there's a lot of like more, I would say, economic incentive, and that's how policymakers usually think about it. The problem is that as soon as that economic incentive goes away, the problem just behaviors just shift back. So our hypothesis was that if we relied on people's internal utilities and motivations, right, because people do want to do good for their environment, they do care about their society. So if we relied on that instead, that would be much more sustainable, because you don't have to like pay or figure out an extra cost to that entire system. You are just leveraging whatever intrinsic values people have. And I really believe that people want to do good for their societies, for their neighbors, for their countries, right? So then trying to figure out how to use that in the nice way is what motivated us to do this thing.
Yeah. That's a really nice hypothesis. I also believe that there is in every single individual there is some altruistic,
Yes.
at least a piece of altruistic behavior. But how did you test this hypothesis? Did you test it?
Yes. So now I'm just going to go, good question. I'll just talk about this choice experiment that we tried to then test. Right. So then we did a mode adoption study. So we have a measure of acceptability. The question is, like, if I use that acceptability measure to then recommend a plan, which is different from someone's usual plan, will they actually adopt it? So we used a choice study we designed a choice study around this system. And I know that there's certain limitations to what a choice study would do. But the problem is, like, if you deploy this in a large city, first of all, the deployment is very costly. And then you aren't able to run very many experiments. So that's why we set up different types of evidence to support this hypothesis, right? The first one is just doing this choice study. So the way we did it was we had two surveys. The first one was a profiler survey in which we asked people, hey, how many trips do you take in a week? And please tell us about one specific trip that you take regularly, right? So people told us about that. And we also measured like what their demographics were, what their education level, things like that whatever was useful in classification of the mode, right? And then we designed this choice study where we said, imagine you're taking your usual trip, right? And we defined what that usual trip people take. So this person goes to a film networking event every Thursday, right? And they leave at 7, they arrive by 7:20. Now for this specific trip, and they said that they drive to this one, we then recommended an alternative route, right? Which was like, hey, will you take a public transit if you had to make this trip? The departure time would be 6:20, you would arrive by 7:10. And then we also grounded this alternative trip into, a map, like a Google map like thing, like we defined like what would they have to do. And then we measure like if they think this trip is reasonable, they're likely to take it. Now, I know that the cost of actually taking a route is different from saying that you would take it, but it's still aligned. That's at least our hope. So we did the study, we measured people. And then we tried to understand the data that we got, right? So the outcome variable is, are people likely to take this route? The independent variable is how acceptable this route was given our formulation of acceptability. So again, like we have the dependent variable, which is adoption, like do the people take the route or not? And so we did two different things. We did the ordinal adoption, which is the Likert scale measurement, and then the binary adoption. So if anything was greater than 0, that means that they are taking it. If it was less than 0, it was not taking it, right? And then the independent variables, we had 3 different definitions of acceptability. So one was switching gain that I was talking about. Then others is the odds ratio. Then the other is just pure probability, right? Whatever the classifier was giving us. And then we did find that the best definition for acceptability was the odds ratio, right? So the way you would see it is it's statistically significant and also has high coverage of the variability in the data. So we then said that, okay, then odds is a good definition to go. It captures if people would actually take the route or not. So again, like some takeaways, definition of acceptability works. Our hypothesis was if we gave people a route that was more acceptable to them, they would take it, or at least they'll say that they'll take it. And it seems like, yes, they will, statistically significant. And then the odds is the probability of their adoption. And the impact was small, right? So the number that we are here looking at is pretty small, but then it's statistically significant. So at least some people are aligned with this definition. Okay, so finally, now we have a definition of acceptability. How do we integrate with planning? So we came up with the process, and again, it's defined in the paper in much more detail. So first, you generate a mode candidate set for Dr. Jane, right? So we learn from Dr. Jane. We can just ask her, right? Can she walk? Does she take the bus? Is subway accessible to her? So that gives her a set of mode set that she can take. Then the second thing is to translate this into a regular expression that for valid plan. So this is just constraining the search over the graph, right? Then we compute the most time efficient plan, because the assumption is everyone would rather go get to their destination quickly than later. We compute energy reductions in each plan using an energy model. So our previous work actually simulated how much energy people take when they are taking the bus versus taking a car. So we had mathematical models that were defining energy consumption on each edge. So we compute the plan, we compute energy reduction for each plan. Then we evaluate the likelihood of adoption, right? If the energy reduced plan is actually something they would take or not. And once you do those computations, you can figure out which plan has the maximal expected energy savings given our given our model of adoption, like given our understanding that how people accept these plans, can we compute the maximal energy saving plan. So again, like you're seeing this sort of pull from both sides, right? We are doing the system level optimization from energy, but then we are putting this constraint that we still want to keep the plan acceptable to people, right? So it has these constraints coming in from two directions, and if you apply those constraints, at some point you'll get to a point where it's good for everyone, right? It's good for energy, it's good for people. So it's that bi-directional approach to optimization that we took in the paper.
Yeah, can I interrupt you
Yes.
here? And
Yes.
Regarding this, because we have a question, can you does this slide elaborate on the stages of the prediction, or can you just slightly little bit once again and briefly go over the prediction stages?
The prediction stages, okay. So remember, we have Dr. Jane that we are trying to plan for, right? And she has a mode set that's defined for her. So maybe she can walk. She has a bus station is close by, a subway station is close by. So there's 3 different things that she can do when she's going somewhere, right? And any combinations of these, right? So you could have her walk to the bus station and then walk again, right? So that's a possible plan that you can for her. So there's this regular expression. This is just a mathematical language to define the constraints, right? Because if she cannot, if she doesn't have a bike, then you cannot be proposing to her a plan that has a bike for it, right? So there's a full graph, right, which is full multimodal. Then you apply these constraints which are specific to Dr. Jane, and you get rid of the parts which are not possible for her, right? So anything that has a bike in it is not a valid plan for her. So that's the next stage of prediction. The third thing is, it's typical, planning. Like you want to come up with the most time efficient plan, right? You don't want to make her late. You want to do what is the best for her. Then we have to, with all the time efficient plans, you have to figure out how much energy reduction she's going to have given a set of energy models. So the energy models is out of scope for this talk, but then you could imagine that if you had to go from point A to point B with car, we had a mathematical formulation of how much energy that would be versus if someone took the bus, right? So every edge has some energy cost, and together the full plan would have a full estimate of energy, right? And now you have different plans that she can take. You have the energy reductions for her. You want to select the plan that she's most likely to take, right? Because if you don't, then she will say, okay, I don't want this plan. This is not good enough for me. So that's where her internal utility comes in. You know what her internal utility is given every plan, which is what we computed until now. So you then pick the plan that is, saves her energy, but also is likely to be adopted by Dr. Jane. So that's the final stage of prediction. That's the one that we want to recommend. Okay. So the way now the thing is that we have developed this multimodal planning problem. we have a multimodal planner, we have some understanding of how to understand Dr. Jane's internal utility. The question is like, is this even going to work? Like, we have all of these pieces. Will this, our overall goal is to reduce the energy consumption of a city, right? So does this even help? So the way we did this is through a simulation study. It's usually called an agent-based model, in which you would simulate, decision making for every agent in that city. Right, so here the agents are, traveling. So we had the morning traffic and the evening traffic monitored. We modeled 170,000 roadway links, 1 million daily transit trips, and this is the state-of-art simulation model for LA that we built as a part of the project. And then we assume that maybe 10% of this population that's traveling can be influenced. Right, so those are the people who we send our messages to or send our recommendations to. So that was our experimental condition. So with that and the adoption model that we had, we were able to show that if the adoption models are correct, you would actually see a reduction in fuel usage. You would actually see a reduction in the delays, right? So 20% delay is a really big thing. Same behavior in the AM traffic, morning traffic, and the evening traffic. And then this is like how the mode share of influenced people change, right? So all these influenced people were assumed to be taking the car before they were influenced. But if our adoption models are correct, right, our acceptability model is correct, our adoption model is correct, then we can see that people will shift to walking, bike, bus, trains, which are more sustainable modes of transport. So if we did a great job in defining the acceptability problem, there is evidence that people will shift towards more sustainable transportation. So that was the final outcome that we presented in the paper. So again, a brief summary, right? The paper defines the influence problem. It takes the humans of the system really seriously. Like, we are not doing energy optimization for cities. We are doing energy optimization for people. We want to understand what the internal utility, the internal incentives are, and we want to bias plan selection using that information, right? We developed an approach for acceptable planning, which is how do we combine multimodal planning with choice theory to then figure out this acceptable planning framework. We demonstrated that if all these things are correct, we expect to see 4% energy savings, 20% time savings. And then what's really cool about this is this interdisciplinary approach to AI systems, right? It's not machine learning only, it's not economics only, it's not transportation only, but it's trying to put these pieces together from different disciplines into building a system that then can be used, right? As Jiri pointed out, for maybe policy makers who can study like, hey, if I change this incentive in this way, if I change the transportation network, if I build more routes here, then how will the population shift? How will their behavior shift? So it gives policymakers a higher level analysis of how the environment will evolve if things would change. So, right, you can imagine this counterfactual reasoning that policymakers can do using this system. Right, but then this is again a small effort. There were other parts of the problem that we didn't study. I think one of the big things is does this even work in the real world? We don't know yet, because it's a pretty significant system to build and put out. We don't know yet, but I'm hopeful that some of these methods would actually work. Okay, just wanted to thank some colleagues and the funding agency. This work was supported by ARPA-E, which is the energy research department of the United States government, and then Xerox paid part of it because Xerox was the transition partner who was exploring if they could take the technology to market. And then I can just stop here. I just wanted to stress about this really core problem of what I call humans of AI. That AI and machine learning is not just about computer vision, NLP, or games. Those tend to be the typical applications for AI. But I think that really cool, hard, challenging problems exist out of these domains, right? Here we were looking at transportation, but then health. And other domains have really cool AI problems, and I wish that everyone could focus on all these more social good problems than just games, because games are fun to do and I have done research on them, but we should be thinking about how this impacts our society. The second point is we have to look beyond prediction, because prediction is only one part of decision making. We have to study the whole decision making loop and then figure out different ways AI systems can support human decision making. And then we want to think about improving problem domain equity. Like, again, it's going back to, like, games only affect small part of our society. But if we really want to do well for our society, we have to think about how these methods can be, developed to support people who may not have access to resources, right? So maternal health care in India, robust agricultural policy in India, improving education and training in the US. Like, we have to think about how AI systems can solve these really important problems. And I think they can. We have to start working in that direction. Cool. Thank you, Jiri, and thank you, Aggregate Intellect, for giving me this opportunity.
Thank you, Shiwali, for your quite engaging and exciting presentation. I already received some comments here that this is a really cool work. One person shared. Just let me plug my computer.
Okay.
And thank you for this. And I also have some questions.
Yeah. Go ahead.
So first, I would like to engage or ask the audience to raise any questions.
Yeah.
But you mentioned that there were previous experiments with the agents that would predict that 10% of people would actually accept.
Right. No. No. So I'll correct you slightly. 10% of the people would be sent the message to influence them, and out of that, we had the adoption model, right? It said that how people are likely to accept whatever is recommended. So if you sent the recommendation to 10% of the people, only a few of them would accept the option. But even with a few of them, you can get some savings, right? That is how typically this would happen. Mm-hmm. You would try to influence a wider set of people. Most of them wouldn't take the recommendation. Some of them would. But if you target it to the right people, the more people you can actually influence, right? So then figuring out who is the right person to target with what message is useful.
Yes, sounds good. And also, you at the very beginning of your presentation, you mentioned the competition Transnet, right?
Yes.
And
yes.
You were specific that your group or you actually choose a different approach than the others. So can you try or can you give us an idea what other teams were doing?
Right. So this is, if I communicated that this was a competition, I miscommunicated. This was a grant, right? So the government agency will say, hey, we want this problem solved. What are the different approaches to solve this problem? And we were one of the people who, got the grant. There were other companies, and I think a lot of the other companies were driven by economic models, but they were trying to figure out the right incentivization schemes, right? Mm-hmm. The monetary incentivization. The way we were different was relying on this internal utility of people and then trying to estimate it and then using that to influence them. That's how we would, because a lot of the times when economists usually think about it, they always think about, hey, what incentivization structures can we put? Like, can we incentivize people's companies to then incentivize people to take the bus, for example. Like, that's a genuine policy approach, and it's pretty effective. We were going at it from a very different perspective, like relying on people's internal motivations and incentives.
Okay, yeah. So before I ask you another question, I got a question about if you are open to connect over your email and are open for a collaboration.
Yes, I am. My contact info is right on the slide. I'm Shiwali Mohan on Twitter, shiwali.mohan@parc.com and shiwali.mohan@gmail.com. So please feel free to contact me. PARC research is a very collaborative space, and we are continuously looking for partners, both the government and the other industry. Sometimes, it could be that Xerox cannot take certain solutions to market because it's not their business. So we are open to connecting with other industries who are interested in this problem and can take some of our methods to market. We really specialize in doing this translational research where we start from an academic understanding of the problem and then try to do a more applications practical approach that can be put into systems out there. So we do this part, we do de-risk some of this technology, hoping that some industry partner can take this to market. So I'm very excited about collaborative opportunities.
Yeah, that's awesome that we we have or we ACE facilitate talks with researchers like yourself, and people already ask questions like that in the chat. So
Yes.
I'm very happy for facilitating such.
I'm very grateful for Aggregate Intellect to providing this mouthpiece to get in touch with so many different people. Very, very appreciative. Thank you, Jiri, for inviting me.
No problem. And Shiwali, did you also bring or take any inspiration in other similar problems where products or machine learning solutions would try to provide its users with alternatives or
Yes.
acceptability?
Yes. Yeah. So the other problem that I personally worked on, and I'm still working on, other problems of similar nature, but the one that I was very excited and proud about was building this coaching agent for people to develop like new, healthier behaviors, right? So one of the bigger problems that's emerging right now is that people are very sedentary. Mm-hmm. And that then causes like increase in hypertension, diabetes, and a lot of other things, which is very costly for the health system. So our idea was that, hey, and the people like are unable, people don't find enough support system to actually start exercising. I believe that people want to live healthier lives, but there isn't a lot of support system, right? Because if you had to go to a nutritional coach or an exercise coach, it's very expensive. So only few people can access it. Most people cannot. So we were trying to figure out, how can we use AI machine learning methods to then develop a coach for people who may not have access to, individual coaches, right? And we focused on, the most important exercise, most beneficial is walking. And the American Heart Association says you have to be walking at moderate to, in a moderate intensity 3 to 5 times a week to then reduce the risk of diabetes and hypertension and other kinds of problems in your life. The question is, someone who has never walked, in their lives, how would they walk this much? So then we developed this model that helped people, slowly climb up this chain over 6 weeks. And this was exciting about it because usually when you think about AI systems, machine learning methods, they're very transactional, like they're one-step process, right? You searched for a query, it gave you an answer, you gave it a computer a picture, it gave you a label, right? This one-time transactional thing. Here the problem is more long-term, where you have to because behaviors don't get built in a day, they take a while, right? You have to do the same thing over and over again. So that was exciting because then that meant that we have to measure people for every day for 6 weeks, and we actually demonstrated in a clinical population that you can support people's healthier behaviors by building a coach that lives on your mobile phone. So that was also very exciting and personally very satisfying to me as an AI scientist, because eventually I want to build systems that help people in their goals and not more autonomous weapon, like some things like a military would try to deploy. So as an AI scientist, that gives me a lot of value. But thank you for asking me that question, Jiri.
Yeah, no worries. I recently also heard about a company that tries to minimize waste, just waste or garbage. And they developed the recommender system how to engage people to recycle more, and which is similar to the domain you actually the domain you actually developed a solution like this. And
no, there are definitely a lot of such problems, and I think we all should be. I'm excited that you were excited to read about that problem. We should be working on those problems as a society.
Yeah, and Shiwali, can you also briefly explain why you were not able to apply the choice theory, or more precisely, why the theory doesn't suggest how mode alternatives cannot be generated?
Okay, so there were a couple of challenges in applying the choice theory as it is, right? So choice theory tells you how people predict or people make choices. So it's a prediction. It tries to get you to some understanding of prediction over choices. Um, that by itself can't really tell you how to go from point A to point B, right? It can tell you, okay, this person may very likely to choose a bus, but then we were trying to build a specific recommendation system, so we couldn't just use that. So we had to go to a planning approach, which actually tells you, like if you look at Google Maps, it tells you, okay, from this time to this time, go to this intersection, then take the right. Like, so we wanted to solve that problem. So that was the one thing that choice theory couldn't take. So we had to like figure out how to put them together. The second thing is that choice theory, the way those models are usually built, are like they're linear regression, logistic regression models, and they only look at a small number of independent variables, right? Because that's what those models can handle. If you really consider a human, it's not just like, the time, the cost, it's also a lot of other things. Like it just could be my education, it could be how many people live in my home. Like there are all these other factors. And the more you put the factor you put onto this model, the classical model will have problems computing it. So then going to a more machine learning based model, saying that prediction is actually useful for the choices, like you can then take all these different features, a bigger feature vector, a larger data set to then solve it. So there were two different reasons to why choice theory by itself or those models are not useful, but it was also the central insight, right? It was a central guiding force. Like we designed the entire system assuming that choice theory is actually the correct way of representing it. So everything is designed around it. It's just that we won't use the same model.
I see. Yeah, thank you for the answer. And the very last one, from because you said that at the end of your paper you said that you would like to integrate the results with additional alternatives and eco-routing feedback control.
Right.
You mentioned
Yeah.
that would be selecting driving roads based on the real time link estimates for the fuel
Right.
content.
Right.
How does it go? Or do
I
you?
mean, one way to think about like the online feedback thing is that if you do this data set analysis and figure out the predictive model, it's a good starting point for Dr. Jane, right? But then Dr. Jane's behavior, if we observe it multiple times, right, then we can actually do a better prediction, better choice understanding for her. So then that was the idea that we were thinking of exploring, is that once Dr. Jane gets into the system, then we can, like every day, we can track what she did and then do a choice theoretic thing for specific to Dr. Jane, as opposed to doing it over the full population. That was one point. The other thing is the transportation route modeling, the energy modeling is all done like a priori to the system. But if you built out a system, then you would have more real-time data. You would have things like, hey, road from this intersection to this intersection is congested, so it will take longer, which means that then you have to reroute the traffic. This would be like a typical what Google Map does.
I see. Thank you, and I wish you good luck if you elaborate even more on your work.
Yeah, cool. Thank you, Jiri, for
I think
asking
people
me to
very
come
like
here.
it.
Yeah.
Once again, thank you. I would like I just want to conclude or
Okay.
summarize the work. So Shiwali was so kind to tell her about her work, how to design basically a recommender application that would calculate the accept, or they would elaborate on acceptability of its users and design acceptable alternatives to their choices of commuting, or alternatives of possibilities of commuting. And such work can lead to much lower negative externalities produced by these individuals, and especially in large cities where commuting is behavior any individual exhibits. And this also affects others, because it creates traffic jams and pollutes the air, and not to mention that the expenditures of transportation is huge. So that's the work she mainly introduced us today. Did I forget something to mention, or would
No,
I?
I think you got it. Thank you.
Yeah.
Thank you for
So
summarizing. Yeah.
this is it. Shiwali, once again, thank you. This was
Thank you.
awesome. And for those who watched us, make sure you subscribe to our YouTube channel, Machine Learning Papers Explained, to get notified about all the live sessions and other free content we publish. We currently have about 15 different streams that are focused on various machine learning topics, and this session is in machine learning in economic streams. So I hope you enjoyed it and you will come back. Thank you, and good night, everyone.
Yep. Thank you, Jiri. Thank you, Aggregate Intellect.